Hello, we're Terrestrial Robotics at Ohio State, an undergraduate student organization at The Ohio State University, and this is our Rover Cassius, our submission for the 2026 University Rover Challenge.
The chassis of our rover utilizes a rocker mechanism to be able to traverse a variety of uneven terrains, such as sand, large rocks, and even some of our very own Columbus potholes. Our rover includes a 5-axis arm with 1 degree of freedom each for our turret, shoulder joint, and elbow joint, while a differential wrist has 2. Each joint is linked with hollow carbon fiber cylinders, which provide great strength and durability while remaining significantly much more lightweight. To drive the joints, our arm utilizes 2 harmonic drive gearboxes, each of which provide a 100-to-1 gear reduction with minimal backlash, allowing for smooth and precise operation of the arm joints. As part of our rapid prototyping process, our team researched and experimented with carbon fiber infused PETG for 3D printing, which allowed us to create prototypes quickly, while the increased strength compared to standard filaments allowed us to be able to run full-scale tests and demonstrations while we were working to manufacture the permanent components.
This year, we redesigned and manufactured a custom differential gearbox for the wrist of our rover. The gearbox allows for both the roll and the pitch of the rover to be adjusted either independently or simultaneously, giving it 2 degrees of freedom. This gives Cassius flexibility in positioning the end effector. Our end effector is comprised of 2 grippers with custom TPU shells to provide a better grip on objects, which are driven by a lead screw and a stepper motor. The lead screw allows for precise control of the end effector, while the base allows for quick swaps of end effector configurations based on the mission.
As a continuation of prior efforts, a Raspberry Pi 4B is the primary microcontroller of the system and communicates with 3 Adafruit Feather RP2040s to manage the communication system and motor drivers. The rover uses a 14.8-volt LiPo battery as its power source, which is distributed to the Pi and motor drivers through a power distribution panel. The microcontrollers and drivers are hosted safely inside the box to prevent contamination, while wires extend out up the length of the arm to reach the 6 motors utilized for arm control.
To deactivate the rover in case of an emergency, there's an emergency stop button on the side of the box. Alongside this button is a display of the battery's voltage, current draw, and power draw in order to monitor the power supply during usage. The rover uses the Adafruit Ultimate GPS unit, which is capable of tracking over 20 satellites simultaneously and provides the rover's position with a high degree of consistency. To communicate with the ground station, the rover uses a 915 MHz radio antenna, which is capable of maintaining a stable stream of information despite long distances and intervening obstacles.
Our robot integrates both autonomous and manual control capabilities to support complex rover operations. Using Aruco tag detection combined with a spiral search pattern, the rover can identify and localize targets with precision, stopping within 2 meters of the detected tag. For future autonomy, we are developing LiDAR-based mapping and path planning using the A-star search algorithm, enabling the rover to navigate unknown environments and avoid obstacles in real time. We have also incorporated a YOLO-based object detection model to recognize and classify mission-relevant objects such as an orange mallet or a water bottle. In addition to autonomous functionality, the rover supports precise manual control of the robotic arm through a remote interface, allowing accurate and reliable manipulation when operator input is required.
Cassius evaluates site habitability through onboard chemical analysis of soil samples. The primary assay uses Mehlich-3 extraction with the Murphy-Riley reaction to measure bioavailable phosphate. A mixed acid extractant releases phosphate bound within the soil matrix, and the extract then reacts with molybdate reagents to form a blue complex proportional to phosphate concentration. The resulting color intensity is recorded for semi-quantitative analysis. A secondary Radford assay detects soluble proteins as an indicator of biological activity. Soil samples are exposed to Kamasi blue dye, which binds to amino acid residues in proteins and produces a color shift to proportional blue. The resulting color is compared against bovine serum albumin standards to estimate relative protein levels. These assays run in a sealed science box using lead screw actuated syringes that meter regions through Teflon needles into isolated reaction chambers for analysis.
As a team, we are always working to build and improve Cassius, redesigning and building where we can. We hope to see you in the Utah desert.